All right, so as I said, we're going to be discussing section 2.6, implicit differentiation. Let me start by projecting this handout. All right, so a key it takes so long to form up. A key concept is going to be the difference between an equation involving two variables and an equation involving two variables that's been solved for one variable in terms of the other. So, let me set them up. Well, so in this handout, you see in example 1, there's an equation x cubed plus y cubed equals 7. So that's an equation involving x and y. It expresses a relationship between x and y. But it's not written as a function. There's not a variable all by itself on one side and the other stuff on the other side. On the next line, you can see that same equation has been solved for, boy, it's just crazy how long this thing takes to warm up. You can see on this next line, the equation has been solved for y in terms of x. So it's this exact same relationship between x and y, but it's now been presented as a function. Y equals all this junk involving x. So if you know the value of x, you just plug it in and you get y. Now in this next example, x squared plus y squared equals 7, that's also an equation involving x and y. It expresses a relationship between x and y. But it's not presented as a function. It doesn't say y equals blah. And the thing is, you can't solve this equation to say y equals blah, because this is not a function. The graph of this, as you should remember, is a circle. So the graph fails the vertical line test. So for most x values, there's either no y value or there are two y values. There are only two x values where there's just one y value. So you can't solve this equation for y in terms of x. Now, in implicit differentiation, we're going to be interested in having an equation involving x and y, and we want to find dy dx. Now, if you have an equation that can be solved for y in terms of x, so y equals a bunch of junk involving x, then fine, you just take the derivative the normal way. You do dy dx equals d dx of all that junk, and you get the derivative. If the equation cannot be solved for y in terms of x, we can still get an expression for dy dx. It's kind of a surprising thing. It's using a method that's called implicit differentiation. Now the key to this method is you have an equation involving x and y on both sides. And the first thing you're going to do is you're going to take d dx of both sides. You're going to take the derivative of both sides with respect to x. So d dx of the left side equals d dx of the right side. And to do that derivative, you're going to have to keep in mind the difference between taking d dx of x, which is just 1, that's just the power rule, and d dx of y. Well, that's actually, we don't know what y is. Y is not presented as a function of x. So we just have to leave this as y prime. So then we started with that equation involving x and y. If we do this, taking the derivative of both sides with respect to x, we're going to get a new equation involving x and y, and also this new symbol y prime. Now that new equation involving x and y prime, we can solve that for y prime. Turns out you can always solve that equation for y prime. Even though you might not have been able to solve the original equation for y in terms of x, when you take the derivative, you do get an equation involving x and y prime that can be solved for y prime. And what you'll end up with is y prime equals some expression involving not just x, but also y. So the thing is, you start with an equation that is not of the form y equals a bunch of stuff involving x. So when you find the derivative, you're also not going to end up with a derivative expression that just says y prime equals a bunch of stuff involving x. You're going to end up with an equation that says y prime equals a bunch of stuff involving both x and y. So it's going to be kind of a weird new thing. Now keep this handout. Maybe put your name on this handout, because on the back side is the handout we're going to use on Monday. And I 3-hole punched these so you can put these in your binder. If you don't have a binder, grab a binder over there. And we're going to be referring to these on Monday. The back side. Okay, well, I want to do just a couple of examples, and then we'll do our quiz, and we'll start the weekend of studying math. So example 1. Suppose that x and y are related by the equation y cos x equals x squared plus y squared. Find dy dx using implicit differentiation. So I'm going to start by writing down the original equation. With y cos x, leave some space here around these equal signs, equals x squared plus y squared. And then I do step 1. I take the derivative of both sides with respect to x. Now the first line, I just write down that I'm going to be doing that. So I have the left side, and in front of that I park d dx. And I have the right side. I put that in parentheses, and in front of that I park the d dx. Now, all of our derivative rules apply. So this is a product. So I have to use the product rule. So I'm not going to, well, I'm just going to write down what the product rule says. I'm going to do d dx of y, that's the derivative of the first expression, times cos x, plus y times d dx of cos x. On the right side, I'm going to have d dx of x squared plus d dx of y squared. Now the left side's pretty simple. It's just y prime times cos x plus y times minus sine x. I'm going to go ahead and I'm going to put the minus sign out front. I think you will are familiar enough with the derivative of cosine. The derivative of cosine is minus sine, and so that minus ends up in front. And over here, the derivative of x squared is 2x. But the thing is here, the derivative of y squared is not just 2y, because y itself is a function. So I have a function inside of a function. So I could think of this as chain rule details, a chain rule problem. So my inner function is a function of y, and we pretend that it's well, so inner prime, I'm just going to say this way. Inner prime is y prime. Or I'm going to say it's d dx of y, and I'm just going to denote that by y prime. The outer function is empty, and it's parentheses squared. So my outer prime as an empty function is 2 times the parentheses. So I have to think about all that stuff in order to find the derivative of this baby. And so what comes back is plus 2y, y prime. My outer function is 2 times the parentheses. I put my original inner function inside the parentheses, and then I multiply by my inner prime. But I just don't bother with the parentheses. I don't like that, but the book does it this way, so I'm going to mimic the book. So notice, this is our equation involving x and y. Here, over here. Equation involving x and y. And this equation could not be solved for y in terms of x. I mean, if you divide both sides of this equation by cos x, you get just y over here. But there's also a y over here on this side. So you would not be able to solve this for y in terms of x. But what we have now is a new equation involving not just x and y, but also y prime. And we can solve this one for y prime. It always works. So all the stuff that doesn't involve y prime, I'm going to move to this side, and all the stuff that does involve y prime, I'm going to move over to this side. So I have y prime times cos x minus 2y y prime equals, on the other side, 2x plus y sine of x. And I'm going to factor out the y prime times the quantity cos x minus 2y equals 2x plus y sine of x. Divide both sides by that term in parentheses, and I get y prime equals 2x plus y sine x divided by all that junk. Cos x minus 2y. And notice that's an equation of the form y prime equals a bunch of junk involving both x and y. All right, example 2. Suppose x and y are related by this equation. X squared plus xy plus y squared equals 9. Now notice that also cannot be so, since it's an equation involving x and y. it cannot be solved for y in terms of x. The graph of this, I'm sure you remember from high school, is an ellipse. So it fails the vertical line.
Could you explain why you can put y prime out of the bracket, outside of the brackets in this first example?
Yeah, sure. Notice there is a common factor. Y prime times some stuff. Y prime times.
Oh yeah, I didn't see the first. No, my bad. Okay.
I'm sure you're not the only one who didn't see that.
Yeah, no, I got it.
Do that, all of you. If you're confused by something, I guarantee you, you're not the only one confused. And as you know, I make a lot of mistakes, so I should start a cash rewards for catching mistakes. Okay, so the graph of this is an ellipse. It fails the vertical line test, so that's how we know this can't be solved for y. So I'm going to have three questions. A, find y prime using implicit differentiation. And then B, find the equation for the line tangent to the ellipse. At the point minus 3, 3. So x, y equals minus 3, 3. So here we go. And then C, illustrate. Ask your buddy Desmos to illustrate. I haven't yet posted next week's recitation problems, but I will be posting them today, in case you're wondering how to spend your weekend. Remember, the exam had at least one problem that was right off, actually two problems, that were right off of the recitation problem list. So, you know, your command of that material will be much better if you see it more than once. If you work on your homework problems, if you work on these recitation problems before recitation, then you go to recitation, maybe having tried them and succeeded, or maybe having tried them and gotten confused. Either way, you'll get a lot more out of recitation if you prepare. All right, so we're going to follow our method. We have x squared plus xy plus y squared equals 9. And I take the derivative of both sides. So I'll have d dx, parentheses, all the junk on the left, equals d dx of the right side. The right side is easy. That's just 0. The left side, well, let's see. I get d. I'm gonna break this down. Implicit differentiation is like a lot of things. It's a lot of baby steps, but they add up to something that's definitely not a baby step. So I want to encourage you to show the baby steps, because a lot of students find it hard, but a lot of students also just try to do it all in their head. And if you don't try to do it all in your head, I think you'll find it's a lot easier. So we're going to have d dx of xy, and then d dx of y squared. So d dx of x squared, that's the derivative of x squared. That's just a power rule, 2x. And d dx of y squared, we did that over there. We get, by the chain rule, we get 2y y prime. So I'm going to remind you of that. This is the chain rule. And that's equal to 0. Now, what do we do here? Right, because this is a product. We have to sort of think of y as a function. So this is a product. So I have to use the product rule. And I'm going to show it in baby steps. I'm going to have d dx of x times y plus x times d dx of y. That's what the product rule says. So now I can clean this up. D dx of x, well, that's just 1. That's on your handout. You have the derivative of x using the power rule. I get 1 times y, and then I have x times d dx of y, though, is not 1. It's y prime. Plus 2y y prime equals 0. So I get, clean this up a little bit, I get 2x plus y plus x y prime plus 2y y prime equals 0. So again, started with an equation involving x and y that could not be solved for y. We end up with a new equation involving x and y prime, and it can be solved for y prime. Okay, everybody buckle up. The stuff that does not involve y, I'm going to move over to the right side, so it's going to end up over there with a minus sign. Minus 2x minus y. And on the other side, I'm going to have y prime, and notice y prime appears in both of these terms, so I'm going to pull it out. Y prime times the quantity x plus 2y. So here I have a common factor of y prime. You can use your yellow pen, and I factor that out. And then all this stuff that does not involve y prime, all this junk, I moved all of it over here to this side, the minus sign. So then I keep solving. I get y prime equals minus 2x minus y over x plus 2y. And there's the solution to A. Notice that's, again, something of the form y prime equals some junk involving x and y. All right, so question B was to find the equation for the line tangent to the ellipse, that is tangent to the graph of this, at that point. Okay, so the normal, the tangent line equation, or the regular, I should say, regular tangent line equation is this thing. Y minus f of A equals f prime of A times x minus A. That equation is fine when we have a function f. When we have a function f of x, and then we take its derivative and we have a derivative f prime of x. But the thing is, look at our derivative. Our y prime, it's not just a function involving x, it's an expression involving x and y. And also, I don't have an f of x that I can use to get my y values. I have kind of hard to figure out the y values. So for implicit differentiation, we have a known point of tangency and I'm going to use the letters A, comma, B. So our known point of tangency is -3, comma 3. And then we have a slope. M is y prime of AB. So that is y prime is something that depends on x and y. So there's an x and there's a y, and you're going to use those to get your y prime. So using that, I get y minus b equals y prime times x minus a. But maybe I should write this different. I should say the slope is just y prime, which it depends on a and b. I'm just going to use this symbol y prime. So we've got our a. Let's get our parts. We have A, which is known to be the number 3, -3. We have B, which is known to be the number 3. These are given. And then let's use that formula over there to get y prime. So when x equals A, which is equal to -3, and y equals B, which is equal to 3, we get y prime equals that mess. So -2 times -3 minus y, which is -3, divided by x, which is -3, plus 2y, plus 2 times 3. So that's -9 over +9. So that's y prime equals -1. So when I put those parts into the equation, I get y minus my known y value equals my slope -1 times x minus my known x value. So y minus 3 equals minus x plus 3, but that's minus x minus 3. Is that right?
So,
Yeah?
the f prime, -2 times of -3 gives +6. So +6 minus 3 gives +3.
Ah!
On the numerator,
Ah! Well, that's not going to help me, is it? Dang it.
Should just be 3 over.
Yeah.
No negative.
Ah! Good, thank you. It's really too bad I'm not giving cash prizes. So I get y equals x plus 6 is my equation. Now, let's have a look at this. Get our buddy Desmos. So we have x squared plus xy plus y squared equals 9. There's our ellipse, and our point minus 3, 3 is there, and our line is y equals x plus 6. Isn't that amazing? Trust me, it's really cool. There it is. There's our ellipse. There's our point minus 3, 3. There's our tangent line. So notice there's more. You can't just use x equals minus 3 and find y, because there's more than one y value. And notice if I find y prime down here, it's going to be a different value. Y prime down here is going to be a negative number. So the y prime value depends on the x and the y coordinates. All right, let's do our quiz.